Okay, good morning and welcome everyone to SpaceGeekSpeak, AWWII Houston section. We meet every Saturday and we are happy to have you here attending, as well as Charlie Vono. Charlie is a retired US Air Force colonel. He was a strategic air command pilot and an engineer in US Air Force space program. He is also a retired TRW ICBM system engineer. His various presentations include from Oliver Flower Mill to commercial space, in-flight refueling the SR-71 during Cold War, and how Minuteman III ICBM works. He is going to talk about a few things he learned in his career that should be useful to remember in the emerging commercial space industry. Welcome, Charlie, and your floor.
Okay, thanks. I guess let me just mention a couple of things. First off, that I've got my chat box open, but it's going to be real easy for me not to notice questions. So if you want to, stop me for a second and say, hey, there's a question here, and then repeat it for me, that probably will be the best way to do it. Or if you want to let me go for a while and then give me a string of questions, it's up to you, whatever you want to do. But
that's good. We'll see depending on the question, and otherwise we can wait until the end of the presentation.
Well, I like the discussion, and I've got so much to talk about here today that I'm pretty sure I'm not going to get through it all. So let's just enjoy the time we have if you've got a question as we go. And also, I'll just mention that title, The Exponential, the Rabbit Hole, and the Engineer, that refers to the three lessons. We used to call them lessons learned, but nowadays we call them lessons to be learned because we're always remembering that we forgot important lessons. And there's a lot more than three, but I thought if I limited it to three for this morning, we could sort of cover them all and get a good idea. But basically, I'm going to be going through a whole bunch of examples and then talking about these lessons and how they fit in. The exponential, the rabbit hole, and the engineer. So for instance, one way of looking at the exponential is that if you're trying to keep a legacy system operating for decades, like we did with Minuteman III, you're hoping to find your emerging failure modes at the left end of that exponential before they become a huge problem. Because, ICBMs are buried out in remote sites across the northern tier, and everything that you do to keep it going and keep it working has to take into account that remoteness and the need to get out there and have an integrated plan to go upgrade or fix emerging problems that you see. And so I think that's a really good parallel with our emerging commercial space industry, because in addition to, of course, the stuff you'll have up in orbit, you'll have remote sites on the ground that you'll have to keep sustained for decades, simply because, when you go out, and it's like when I was talking to the planetary defense guys in LA, I said, if you build a planetary defense system, you probably want it to keep working the next day and the next year and the next 10 years. And you want to be able to prove to people that it works. So there's a lot of parallels with a lot of these emerging space programs with what we had to figure out back in the 50s, 60s, 70s, 80s, up to today with ICBMs. The second, the rabbit hole reference is this idea that you can't really just launch a few every year and catch things. That's too late. You're not at the left end of that curve if you're doing that. And so the rabbit hole is sort of the your indentured list of parts in your system. And you go down that indenture to get down to the lowest part that you can continue to analyze. So for instance, we found issues with electronics around the let's say 1990, we found issues with electronics in Minuteman II and III. And, by the turn of the century, we were replacing all of the electronics in the guidance system. And the there's a second benefit that you might not think of, which is, well, if the electronics in this part of the missile are bad, are the electronics in this other part of the missile or this part of the ground system, are they having aging or wear issues that are similar that we need to go look at right now? So that's the indenture rabbit hole. And then the engineer, you know, I got the cute little bunny there from the PowerPoint clip art to represent the rabbit hole. And then I used my picture from, it was a wonderful trip to Italy back in 2019. That's Tuscany there. And I just used my picture as the engineer. And that's a reminder to say that although, you know, we as engineers have a tendency to think that we can solve anything and we're really super good at what we do, you don't keep a legacy system working for decades with just the engineers. You've got your program managers, your statisticians, your item managers, your logistics, and you all together have to work as a team. And hopefully I'll get to more detail on that in a later chart. So those are the three examples. And before I leave this chart, I want to point out my copyright box at the bottom. I put that there not because I want to limit you on showing this. It's just that I've come up against copyright issues as a speaker, and I want to make sure that I'm clear about the fact that you know, everything that's in here is either my original work or it was something I was allowed to use because I'm not making a profit off of it. So you're more than welcome to use these charts any way you want. You know, just make sure you don't put yourself in a position where you're appear to be making money off of it, because it's in this day and age, there's companies that go out after you if you do that. So I'm giving you the benefit of my experience on that. Who knew that photo of Rick May was copyrighted? So that's my first title chart. And then I'm going to go to another title chart to sort of, let's see if I can make this work. Apparently my buttons aren't working, so I'll hit this. There we go. So this chart, you know, I mentioned in sort of the casual passing that you sort of go down the indenture of your system. And there's a couple of big questions that come up as soon as you say the word system. You know, what system? Where are you drawing the line around your system? What do you think your system is? And a huge part of that is, well, what did you build your system to do? And that's going to tell you, you know, what you need to include in that circle. Like, for instance, in ICBMs, we had a risk management program that covered, you know, what we felt was all of the parts of the system that at least we felt we were responsible for. But if you're going to sustain an ICBM over decades, there are certain pieces, like for instance, the real property at each of the bases, as it turns out, does not easily fall within the system that you're managing. And so you need to invite those people from the bases, the operators, the maintenance, local maintenance folks at those bases to participate in your risk management meeting, because sometimes those, you know, real property items out at the launch facilities can degrade and represent an emerging failure mode that's a threat to your mission. So we always come back to mission. So this chart is meant to say, you know, I like to think of a system as broad a definition as I can, and no matter how broad I get, I find that the lessons I learned from ICBMs and other Air Force weapon systems can be applied there. So for instance, here, I use an example of fiber optics manufacturer in commercial space activities at the bottom center there. And then we expand out to bigger and bigger definitions of systems. Oh, by the way, this is one thing I wanted to mention. And have you guys ever had Justin Kugler come out and talk to you about commercial space? I co-authored a paper with him, and
No, but I would love to have his contact, and we can do it after.
Yeah, if I don't remember, remind me so I can get you two together, because he could really give you some great insights into what his company's doing right now with commercial manufacture in low Earth orbit. So anyways, you see there's a circle there that says space, and I basically think of those as man-made purposeful systems there on the left-hand side. So, but you can expand that into, let's go one level beyond that and say man-made accidental systems. And one of the examples I've got there is the Spanish flu, because my grandmother Concetta died of the Spanish flu in 1918. And that was, you know, they're still studying and trying to understand exactly what happened there, but they're pretty sure that we accidentally created this system to spread a pandemic all across the world, because we were not only moving our soldiers around to support the Great War, but also because it was wartime, we had a tendency to not talk about the plagues and the medical issues of the soldiers, which is, you know, long-standing, hundreds of years of, anytime you've had war, you've had plagues that go along with the soldiers, and you don't talk about it because it reveals your weakness to the enemy. Well, Spain was a neutral nation in that war, and so they talked about it, and so they, just like South Africa nowadays, they got tagged with oh, we're going to call it the Spanish flu, because apparently it must have started there, but who knows where it started. Just like Omicron in South Africa, who knows where it really started, but you know, South Africa was smart enough to be able to see it and tell the world about it. So for their efforts, they get punished. Anyway, man-made accidental systems, Grandma Concetta, Spanish flu. Oh, I wanted to mention, in case you didn't realize, so at that time, my grandmother, grandfather just come over from Calabria. We're living in Des Moines, Iowa, and the grandpa apparently got the virus from working at Fort Des Moines, which was quarantined because of the flu, but they still needed cheap labor, and he was a Italian immigrant, so he was happy to get the job, and they were happy to use him whether it was safe or not. And at that time, we had a nation of 100 million people. Now we have a nation of 330 million people. At that time, about 700,000 people died from the Spanish flu. And, you know, there were a lot of parallels if you wanted to go jump into that. If you're wondering about today's pandemic, there's a lot you can read about yesterday's pandemic, and you know, they had masks, but they didn't have vaccines, and et cetera, et cetera. Then we move on up to non-man-made systems, like, for instance, the Earth's climate, and talk about it exponential. You know, because carbon doesn't come out of the atmosphere as fast as it goes in. It's just a physical phenomena that we understand well. And because we know that more carbon in the atmosphere traps more energy in the atmosphere, again, well understood physical phenomena that we know, what we have a hard time with is figuring out where along that exponential we are right now. And so we're hoping, a lot of people were hoping to catch this at the emerging failure mode stage, where it was small enough to deal with quickly. But I think we're all pretty sure now, or at least those who study it, that we're now into that region of, we're going to have to do some smart stuff, and there's still probably going to be some pain and some risk mitigations to be taken. I would just put in a pitch for, it's the engineers, despite what I say about the engineers on the title page, I think it's the engineers who are going to get us out of this, or maybe the billionaire program managers who have an understanding of engineering, because not all solutions are created equal. And if you have a risk management board to figure out what your risks are and what actions you need to take, well, it's one thing to do that when you've got a colonel sitting at the table that says, we're going to do this, we're not going to do that. And then, a couple of months later, he goes, looks like that was a bad mistake. Now we're going to do this and not do that. You have to be able to make decisions. But basically, we're in a situation with these sort of big, huge systems where the arbitrators are the population, that we have to come up with dozens and dozens of good ideas. And I don't know if y'all remember the famous Winston Churchill quote from World War II. He said that the Americans can always be counted upon to make the right decisions, to take the right course after they've tried everything else. So you have to build that into your model too. So anyway, that's the way I look at systems. And you'll see in a couple of charts here, I've got a lot of background in control theory. And control theory, they always say, identify your system, figure out if it's observable, figure out if it's controllable. And so that's, I think, in terms of systems. And then here's my third introductory chart, which is sort of your classic overview. I'm going to bore you with my career, because I think there are some good examples there, and I enjoy talking about myself. So we'll be talking about how my career helped me understand what systems are, what is a complex system, and then eventually it started to dawn on me what you do to sustain a complex system over many decades. So hopefully we'll get to some of those examples. So the second major bullet is sustaining complex systems, and something that you probably have not heard about before, which I'll talk about, is this systems management degree from USC. In fact, why don't I just talk about it now? The world during the Cold War, the 50s, 60s, 70s, 80s, we're in a Cold War. Air Force officers are placed on alert. They have to be confined to a certain alert facility. If the balloon goes up, then they can run out to their aircraft or be there down in their missile silo in order to provide that effective deterrent. But especially, they're essentially in a situation where they can't really leave that alert facility or leave that missile silo. Yet there's this other thing that they have to do, which is they need to go get a master's degree in order to progress in their career. So arising out of this problem, University of Southern California said, we think we have a solution. We'll create a correspondence course, a master's degree in systems management, because a lot of you are going to wind up managing very complex weapon systems, and we're going to help you do that by helping you with this systems management degree. And so there were thousands of Air Force officers who got that degree, and many of them I worked with. And I got that degree, and many of them I worked with on ICBMs, and that also helped focus us when we're trying to deal with this question of sustaining a complex system. We had this sort of one of the things in our toolkit to use to come up with solutions for that. And so I could brief the whole briefing here from this chart. So let's move forward. I don't know if there's any young people, but whenever I've got young people in the audience, I like to show this picture because I like to encourage them to follow their dreams. And I'll just indulge myself. And for all you folks that are not that young, you might remember in the 50s and 60s when the Air Force would donate a big hulk of aluminum, an old jet that they couldn't use anymore. They'd donate it to some local community. They'd plant it somewhere on a gravel or cement and let the little kids climb all over it and fall off and hurt themselves and break their legs and stuff. And so us older guys like to say, well, we were the tough generation. We were tough enough to do all that. And I mean, you can do that now that you're the guy who survived it and didn't wind up with a concussion. But so that's my memory of that. That's like the 60s. And then the late 70s, I actually got the opportunity to be an Air Force pilot. So that was a wonderful experience. But I guess I could also mention, sort of off topic, that if you were to look in that cockpit, you're not going to find any computer screens. That's really the old school cockpit in there. And then if there are any young folks here, you can go back and look at that and wonder what I meant by this chart. But now I'm going to seem to indulge myself and talk about my family, but I will guarantee you that it is relevant to the topic I'm talking about. The upper left-hand corner there is a picture of my dad, Michael, and his brother, Charles Thomas Bono, which that name should sound familiar. I was named after my uncle. They're shaking hands in the backyard of Michael's house, my house, in Wasco, California, after the war. And they've both survived World War II, and they're living the American dream and raising a family with their own house. In fact, they lived across the alley from each other, so I saw my cousins all the time. But I guess the point of this picture is to sort of remind people of our recent history, and especially explain these two gentlemen had parents who immigrated from Calabria to Des Moines back in the early part of that century. And there's pictures of the 5 kids who survived. So that's Chuck on the left and Mike on the right of those kids. And the 3 girls, there's a girl and a boy who didn't make it to this photo. One died as a baby just before Grandma Concetta died from the flu. And then the older boy died when his orphanage had a trip out to the park, and he drowned in the river. So they're dangerous times. And my dad graduated in 1930, so he was the oldest of them. And so they got to not only be orphans, but be orphans during the Depression. So some rough times. And but Dad tried to stay in touch with all his siblings and try to be a help to them throughout his life. And that's a picture in that same backyard of my dad, my mom, Susan, myself, and Linda. And that's just a couple of years before he passed away in 1956 from heart disease, because he had a difficult, rough life. And you'll see a chart real soon that expands upon that. But fortunately, and indulge me, that's 1998 at the bottom, where my sister Susan and my mom were there for my pinning on ceremony as a full colonel in the Air Force. So that was just a wonderful sort of a flow of the generations. And that really does apply later when I talk about systems and how they all fit together. But this chart really is meant to give you more of my background, my certifications and degrees. That astronautical engineering degree is mostly control theory. That mechanical engineering degree was mostly control theory. And then I talked about systems management. And you see some of the other things I was privileged to be able to do throughout my career. So the beautiful thing about being a systems engineer and being able to do a lot of different things is you expand your systems thinking, which is an important thing to do. In fact, let me give you another example of a system. So here's my dad during World War II. Well, the lower left, he's just gotten home and he's holding, let's see, that would be his niece, Harriet. And on the far right, he's at his business. He was a watchmaker, jeweler back when they had watches that you had to fix. And one of the interesting sidelights of my career is, having been in guidance quite a bit and worked with a lot of other guidance engineers, it seemed like 90% of them, their dads were watchmakers and had jewelry shops or things of that nature. Anyway, the point of this chart isn't any of that. It's the picture in the upper left-hand corner. My dad took that snapshot of V-24 on a mission flying over the Adriatic, heading out to on one of his missions to bomb Romania and take out the Germans' ability to execute an industrial war by taking out their industry. And those airplanes there, you might look at that and think, well, that is a formation of aircraft. But you look up that picture on Wikipedia Commons, and they will talk to you about a combat box. That's a combat box that was especially designed to make these ships, as they called them back then, into a flying fortress. Now, I know the B-17 was called the Flying Fortress, but all of these brand new high-tech all-metal bombers would fly together in a combat box to create a flying fortress, protect each other with those guns. And so what is that? That's a system. And that system is designed to, the mission it's designed to do is to reduce the industrial capability of the enemy during a modern industrial warfare. And so that's a key point to remember. Let's see. Oh, I just mentioned one more thing before I go on to the next chart. If you go to my website, charlesfono.com, and that's listed on that first chart of these charts, you'll find a lot of video voiceovers, a lot of previous presentations you could just pull up and look at. And one of them is Two Brothers from Calabria, which talks about my dad and his brother and their World War II career. So if you wanted to learn more about that, all of these things I talk about here today, probably each one of them represents another either video voiceover or presentation that you could pull up and learn more about if you're curious. And I just do it for the fun of it. So let's see. I want to mention that, and again, this may sound like I'm just enjoying the fact that I'm telling you about my family, but it does lead to discussion about systems. Now, what system did we have going in the Pacific during World War II? Well, World War II in the European theater, you had the Army Air Forces trying to show the world that this newfangled idea of jumping over enemy lines and taking out the adversary's industry, that crazy idea actually would work. That crazy idea came from the 1930s Army Signal Corps when they were looking at the air forces we deployed during the first modern industrial war, the American Civil War, which was the first modern industrial war. And we had air forces there, we had balloons, but they were underutilized. We didn't really have the technology to exploit aviation in World War I, but we tried. And then as the Army Signal Corps is trying to put all this together in their head and decide how you use airplanes in war, they were able to see the Spanish Civil War and how the Germans were using the Blitzkrieg concepts there. So they came up with this idea, and then people like General LeMay showed us that it could work. Now in the Pacific, there's that system in Europe. Now the system in the Pacific really was meant to be, we're going to island hop, and we're going to build up our logistics chain, which is a system, of course, until we get to the point where we're right next to Japan, and we've got the logistics chain to be able to invade and either cause Japan to surrender or take over the country. Just classic warfare. And so my Uncle Chuck was in the midst of that. He was at Pearl Harbor. He was assigned to the New Orleans, and that, if you know your World War II history, the New Orleans was the only ship that was in dry dock. And so it was capable of being, of having the guns work, but the ammunition was down below. And so all of the crew members made a long chain, and they carried the ammunition up to the guns. And meanwhile, the chaplain's standing off to the side, the sky pilot, and says, "Praise the Lord and pass the ammunition," which was a very famous song of that time. And if you haven't listened to it lately, I think you'll enjoy the fact that it's pretty irreverent towards politicians and leaders in the country, and very focused on being a spirited World War II song. But again, sort of digress on that, but the system here was originally intended to prepare for invasion and to soften up the country for invasion, just like we did for D-Day in Europe. We sent General LeMay over with his B-29s and they were pounding the Japanese cities. And basically the same theory that if you take out their industry, you weaken them enough for the invasion to be easier. And unfortunately for the Japanese, a huge amount of their industry was located in these major cities built of wood. And so they were using incendiary bombs, and every night they would fly over 8,000 feet to get that real precise bombing pattern. And 60,000, 80,000, maybe 100,000 civilians might die every night in these raids. And Japan did not decide that that was enough to make them surrender. They just simply started moving people out of the cities, tried to move their industries to places that were more protected. And but in the end, they got sort of what I don't know, maybe this sounds too irreverent for the solemn discussion, but I think of this as sort of the fake because when we hit them with one airplane, one bomb, and took out one city, and then we did it again, the emperor and the top leaders had this sort of ability now to say, we have to surrender because there's no way we can continue. They didn't know that we didn't have any more to expend. So they surrendered, and we saved having to invade. So my Uncle Chuck actually wound up supporting this sort of victory through strategic bombardment. And the reason that's important, that system is important, is because it left us with a new system at the end of the war. Before the war, we were the arsenal of democracy. We built up a system of logistics that was second to none in the world. And we piped that over to Europe, to the Pacific. And there wasn't anybody who was going to fly over all of those two vast oceans and bomb our industry, although we were worried about it, and there was the occasional attack, but we basically were 100% better protected than Germany and Romania and those other Central European industrial areas. And so unfortunately, what we come out of World War II with is this idea that those oceans are no longer a protection. The Russians have a big air fleet. Soon, many other industrialized nations will have big air fleets as big as they care to have. If they ever cared to fly over and bomb us, they could. And there were a lot of people in the late 40s, early 50s trying to explain, we were much more vulnerable than people thought we were. But it wasn't until Sputnik flew over, 1956, I think it was, that everybody really started to wake up, be concerned about this, and thus we went into the period of deterrence and the Cold War. Now, you might think that I've gotten all that out of my system and I've given you enough history about the world history and industry that I've sort of explained systems enough, but no, this next chart, I'm going back to the start of the Industrial Revolution to draw some more parallels. And so bear with me. Is there any point at which I should slow down? And counter value was a nice way of saying killing civilians. Well, in both cases, the reason I was emphasizing taking out the industry is because the mission of this system was to take out the industry. And if you look throughout the history of warfare, like the Spanish Civil War, like the Battle of Britain, like Dresden, what you find is that when you have a mission of just destroying population centers, that may feel like you're doing something useful, but it doesn't really win the war. You have to attack the ability of the nation to be an industrialized nation. So for instance, let me give you an example on Japan. Post-war, they did an analysis. Well, in fact, let me just back up a little bit further and say when we first started bombing in Europe, we weren't exactly sure what the right targets would be. By the end of the war, we realized that oil refineries and rail yards and ball bearing plants gave us our biggest payoff. And so we were focused on those towards the end of the war. Beginning of the war, you had people like, I think this was mostly a British idea that to go firebomb Dresden, let's go take out Dresden. Well, why take out a city and kill all the civilians? Is it really going to be that effective? And so what you see is when you do that is you're not really reducing the enemy's ability to wage the war. What you're doing is you're giving them 1,000, 1 million more reasons to continue to wage the war, to be stubborn. And a good example of that is Japan, where post-war, when we did a lot of analysis of the targets, we decided that maybe a better approach might have been to really hit the rail yards and the waterways very, very hard, and not as much the cities, that might have been much more effective against their industry. But this is theory that military officers study. Let's see. Yeah, somebody says demoralization, but it doesn't really demoralize people as much as it pisses them off. Are there any other questions that I should try to answer at this point?
Larry has a raised hand, but I'm not sure if he can speak.
It says, will global warming be manageable if China or India does not control their CO2 emissions? True story. I mean, it's a very complex system. It's a very complicated solution. So let me just say right now, the difference between a complicated system and a complex system is, in a complex system, you can find yourself in a state that was unexpected, which is why we invented fail-safe in the deterrence era. ICBMs certainly are complex systems that certainly could fail in an unexpected state, but they have a lot of fail-safe guards to make sure that our use of nuclear weapons is safe and sure. But I can't guarantee other countries' ability to do that. Now, talk about other countries and climate. Yeah, there's a lot of complexity here, because if we decide in America that we're just going to shut down a lot of our fossil fuel production in order to save the planet, does that simply mean that we're buying dirtier fuel on the world market? And we probably would have been better off to continue to use our cleaner methods to extract fuel here. Is it important that we look for things that we didn't really realize were green sources until now? Like Michael Schellenberger has taught us that nuclear power plants are green sources and much less dirty than you think they are. And for that example, you can compare Germany and France, and that'll tell you what you need to know about whether we ought to have more nuclear power plants. And so the question Larry brings up, of course, is the difficult one, which says, are we going to convince the rest of the world to not have cheap energy now that we've used all this cheap energy to get to our first world status? Practically speaking, we're not going to be able to convince them of that. So what can we do? We can continue to try to develop clean methods of energy production and share those with people and help them to get to the same level we're at. And there's a payoff there, because there have been studies that indicate that if you keep people at a third world or a second world level, all they will do is continue, no matter what you try to do, all they will do is continue to strive to achieve first world status, and they will generate a lot of carbon doing that. But if you help raise them up to that first world status by sharing your technology and helping them get there quicker, it's the first world countries that are doing the most to try to save the atmosphere. And so the one thing we definitely don't want to do is come up with a scheme that destroys the world economy and keeps the first world billionaires from building vast CO2 farming structures, or whatever the solution turns out to be. Now, having said all that, China is building a lot more nuclear reactors than we are. So they're aware and they understand the problem, but their priority is if they don't raise their population up to first world status, they won't be in charge anymore. And so the Chinese leaders, for instance, are always a little bit afraid of their own population if they're not taking care of them. So that's kind of a complicated answer to a question which is even more complex than I talked about here, but maybe let's just move on to the next chart and interrupt me if there's another question.
Well, I don't have a question, but I have a comment on this chart, and that is, I don't know if you're aware that Winston Churchill, you mentioned Winston Churchill before, he wrote 4 books about the war, World War II, and I read the first book called Gathering Storms, and in that book, he identified various things that happened before the war started that occurred that were actually red flags to an eventual conflict. And I read that book, back in the 60s, so I don't remember too much of it, but I do remember that he outlined a number of areas that could have been noticed before and could have identified that a war was coming. And he identified elements to what happened. And like one of them was one country would have a treaty with another country that if they were to go to war with some other country, that this country would then back up the other country to go to war also. And so it was like and the whole system of countries were doing this, having treaties with one another that said, if you go to war, then I'll go to war to back you up. Or if they go to war here, I'll go to war there. And so it was like
a lot of times those were secret.
Pardon?
And a lot of times those were secret.
It was secret and it was buried. So nobody really knew what was going on. But after the war, he figured all this out and discovered that this was like a time bomb, that you lit a fuse in one little part of it and bang, the whole thing would explode.
Yeah, it's a complex system that was bound to fail in a very bad way.
Yeah. So that was something he contributed at that time, which was very interesting. So I just thought I'd throw that in.
Nowadays, the State Department tries to make sure they understand who's going to help who and try to have multi-nation treaties and things like that to avoid that.
Absolutely. So that was one lesson
type of thing.
So that was one lesson learned coming out of the Second World War, is those complex treaties and secret treaties that existed need to be elevated and need to be transparent, so we all know what's going on, or the countries.
Yeah, kind of like the Dr. Strangelove. You don't build a doomsday weapon and then don't tell anybody about it.
Right. It doesn't work. Exactly.
So let me just mention a few things on this chart, because you might want to go pull up my Evans flour mill and commercial space presentation. The reason I mention Oliver Evans here, and notice at the bottom, I've got 4 books that I think you would get something out of if any of these topics here scratch an itch. So Evans flour mill is widely considered to be the first modern factory. 1790s, Oliver Evans comes up with a lot of new inventions, great inventions of making individual things within flour mills work better, and eliminating some labor, having all the same power source, and then put together in a systematic way. So the grain comes in this end and a very high quality product comes out the other end. Well, one of George Washington's duties as president was to sign off on patents. And when he saw this patent, I think it was either patent 2 or 3, he signed off on it and got a hold of Oliver Evans and said, build me one of these mills at Mount Vernon. And so you can either go to Mount Vernon now, or you can pull up your YouTube videos and see a working Oliver Evans flour mill. And the presentation I have draws parallels between this systemic way of producing high quality flour in a very efficient way, and all of the ins and outs of that, that parallel greatly what we're currently doing or trying to do with low Earth orbit commercial space. And then the next big historical thing I want to mention is that, Bell Labs, which is creating this vast network of telephones across the US, FDR taps them and says, we've got a lot of high-tech stuff we need to work for us to win World War II. You're going to help us make sure all these projects work. At one point, they had 2,000 fairly complicated projects that they were hustling through and trying to get to the point where they would be useful. Like, for instance, the radar I mentioned. Did I mention the radar earlier? With my dad would wind up in a side gun once in a while and not in that ball. And because they would have these things called Mickey ships, which were highly, highly classified, it turns out they would replace that ball turret with a radar. And so Bell Labs invents systems engineering in World War II. And we talked about Curtis LeMay a little bit. We'll talk about him a little bit more later. But after the war, we have TRW and the Air Force working to develop ICBMs. And TRW is a company that was formed to take this concept of systems engineering that Bell Labs birthed and mature it, because you needed something like that in order to successfully create and deploy ICBMs for a deterrent against the fact that we no longer had the oceans protecting us. And so you think of that as sort of the teenage years of systems engineering. You look at systems engineering today, and it's so far advanced in a lot of computerized models and things like that, but it pays to go back and look at the original thoughts of the Bell Labs, the original thoughts of these TRW engineers in developing this. For instance, what's your system? What's your mission? What's your requirement for that mission? And how does it go down the rabbit hole to fit this requirement for this particular piece on the system? And how do you validate that you met that requirement when you design, develop, and deploy that? That's very, fundamental things to systems engineering that you can't forget, just because we've got a lot of fancy models nowadays that work really, really great. And then I think I've covered the rest of that earlier, so let's move forward. We're getting close to an hour, and I'm like chart 6 on 20 charts. So I don't know if you want me to come back next week, but I'll just try to keep giving you examples until you get tired of me talking. As
we can, Charlie, we can limit to, let's say, to 1 hour and 20 minutes and leave some for maybe follow-up conversation. And then next week, you're welcome to come back and it will be perfect.
Okay, we'll do that, because I really don't want to rush through this, because then you'll just wonder what it was I said. I'm trying to make sure I'm sort of building this picture and drawing an explanation of why it's so important to see those emerging failure modes as they come out, why you need to go down that indenture, why it's important to have teams instead of just the engineer. And there's just throwing out a lot of examples as we go here to get to that point. Not to say that there aren't a lot of other important lessons learned through this process, but those I limited myself to those 3 because I'm even not going to get through it with this. But talking about, again, we're talking about history here, and this idea that TRW was a company created to provide systems engineering to the Air Force. In fact, when I joined TRW in the mid-1980s, that was just about the time where we were going from rapid prototypes to a sustainment phase, and we were struggling with this idea like Oliver Evans did. We've got all of these individual things that we put together to help us sustain this complex system, but we really need to put them all together into a systemic way of approaching this to have the best flower come out the other end, and to fulfill our requirement to be good sustainment engineers. I guess I should mention at this point, because a lot of people might not know this, but back that period of time in the 1980s, I probably also should mention this. I'll back up even more and say that I'm saying a lot of good things about TRW. Over in the Navy had the very same problem. They were trying to develop sea-launched ballistic missiles. They knew they needed systems engineering to do that, but they focused more on training and upgrading their naval officers in the art of systems engineering rather than hiring a company. And when I was hired in the 1980s, TRW was still providing that systems engineering and technical assistance. I mean, to the extent that, for instance, if my customer had a particular thing that they needed to do as part of their job, I would wind up, what we used to call it, giving them an example of what they could send. In other words, I would take an Air Force letterhead, I would write the entire letter, take it to them, explain why they needed to sign it, and then they would sign it and send it out. That's how connected TRW was from the 50s to the mid 80s in terms of providing probably a bit more than technical assistance. We probably were providing a little too much technical direction for the good of the Air Force. And since then, the Air Force looked at the Navy and sort of turned that around and said, we really need to be capturing the systems engineering expertise and ICBM expertise within our own teams and not continue to pay other companies to do that. So that's a whole nother story, but it's an important systems engineering story, because right here in the mid 80s was when we started to walk out of the rapid prototypes. This ICBM, that one didn't work so good. Let's build this one. Like Minuteman I was a huge leap forward because it had solid fuel, but it wasn't quite there. Minuteman II was, but Minuteman III was much more highly sustainable. So in fact, Minuteman III, although deployed in the early 1970s, is still out there today and is the one that we're about to replace with the GBSD. So the point of all that is to say that that we were moving from rapid prototyping and designs, and you had a systems command which had a location at Norton Air Force Base, which was the ballistic missile office that created all of these sort of rapid prototypes, if you want to call them that, of ICBMs. And they were very focused on meeting the mission as fast as they could with the best technology they had at the time. Get around the mid 1980s, and what's happening is you are moving these weapon systems from development into sustainment. And so Air Force Systems Command would sort of throw it over the fence to Air Force Logistics Command at Hill Air Force Base, Utah, who would be responsible. Okay, now we've got it all built. All you got to do is keep it working, which is like, you know, an early version of people saying you never need software maintenance because you already wrote the software. Of course, there's going to be emerging failure modes. There's going to be problems, and not just mundane problems like obsolescence of parts, but failure modes that emerge that you never even guessed would happen when you keep a complex system working for decade after decade after decade. So the experts there at Hill Air Force Base at TRW and all the associated contractors were working hard to come up with a systemic way to find these emerging failure modes. And I think what I'll do is stop. A good place to stop and take questions is once I explain this chart. This chart is a model that that I developed to sort of take what we learned in ICBMs and generalize it to any system. And you see right in the middle of that chart is a box that says identify risks. Let me just say that I could talk for an hour on this chart and all the details that are in here and why this works for multi-decade sustainment. But it should be, you know, one of the things that we try to do with this approach is to keep it simple enough so that every single new person that comes into our team, we can explain to them what sustainment is and what their job is within the sustainment team. And so we try to keep the concept simple, but each individual part depends on the other parts. And you can see, depending on what part you land on, what your goes intos and what your goes outas are and what you should be doing. So for instance, you have a monthly risk meeting where you review risks, and hopefully your whole team who had their risk meeting the week before, like for instance, the propulsion guys, the guidance guys, the reentry system guys, the ground system guys, they all had their earlier risk meetings where they decided that they were seeing an emerging failure mode that they needed to tell the top guys about. And every month we would discuss these emerging failure modes, these risks, the potential risk mitigations, and that would give us a forum to be able to come up with a list of risks. Now, very important piece, I wanted to make sure I got to this for Mike, because I talked to Mike earlier and said there's a very critical difference between a sustainment risk management board and a sustainment risk management board and a design, production, deployment risk management board. On the early part of a weapons system or any system, you have a pretty solid idea of what your schedule is, and you know how much trouble you're going to get into if you don't meet that schedule. But when you're in the sustainment phase with your risk system, you have to not only identify risks like you did before in terms of impacts and probability, but you also have to determine when it's going to be a problem for you, because you have to create that sort of integrated schedule of going out to those remote sites to put in whatever fixes that you've lined up to get fixed before they become a problem. Before, for instance, you launch a missile out of Vandenberg that fails. You know, you're way too late when that happens. So there's that identify risk. Leading into that identify risk is the observe readiness, or in other words, you've got a complex system here, and if you can observe it, hopefully you have a chance to control it. So you're observing what you're seeing and trying to find these emerging failure modes. So you get to that third part, which is fix the system. And then again, I could talk a lot about how that works, but before I leave, before I take questions, I want to say one more thing, and that is, for this system to work, you need those three things in the lower right-hand corner. You need people who are willing to speak up when they see something that looks funny, you know, and that, you know, parallel with that is you need leaders that don't shoot the messenger. You need, and we're talking about 50s, 60s, 70s here, where we're pulling together all this information. In the 80s, we're starting to really come up with the databases that can hold this on computers. And so you're handling huge amounts of data. You need to be able to have a system that takes all that data and provides the tools to be able to look at it. And of course, the third one there is that if you don't have disciplined processes, you're going to look at decades worth of data and ask yourself, well, did I run this test the same in 1970 than I'm running it in 1990? Can I even compare these two pieces of data? You can't unless you've got disciplined processes. So I think I'll leave it there for just some Q&A and other discussion, and we could talk, you know, try to get up to the present day here next week.
Well, I have one comment there, and then to support your point about timing, and that's very true. There's three elements to a risk. One element is how much impact it would bring to your program or your project and goals. The second element is the probability that that would happen. And the third element is timing. If that impact and probability won't happen for 5 years from now, a lot of things will change in 5 years. So it doesn't make sense to spend resources on it now when you might want to consider to review it on a timely basis. But if the timing is such that it'll happen tomorrow, then that elevates the priority and makes your decision to spend resources a little bit different. I think
I agree with you, except that I'm not sure I'd say 5 years out is a long time.
Well, it's right. It depends on your it depends on your program and your project and goals and everything else, what you're looking at.
Yeah.
But the people on your lower right-hand corner, the people is very important, because when you want to identify the impact, the probability and the timing, where do you find those answers? Where do you go? And most people think, well, the manager of the program knows all that. Not true. Where you go is the people that are are experts in that field, the system matter experts, SMEs.
Mike, I've got a wonderful story. I really hope I have time to tell you right now. So can I interrupt you and tell that story?
Yeah. Oh, absolutely.
Okay, so my friend Marty, who he actually eventually, wound up in the front office because he's such a smart guy, good program manager, smart engineer. Well, one of the things that he was in charge of back in, say, this was maybe 1990 sometime, he had an assignment where he kept track of batteries. There's just a large number of batteries in ICBMs, and our ground systems manager always used to say, buy a battery, buy a problem, because there were always issues that we had to keep an eye on with batteries. So Marty was in charge of keeping an eye on, as the TRW systems engineer, keeping an eye on how Hill Air Force Base was testing these batteries to make sure that he understood that they were being tested the same way they'd always been tested. If there were differences, that he could explain those differences, that he could sort of predict the future based upon the physical characteristics of this battery. And so he had a really good working relationship with the guys at Hill Air Force Base that tested the batteries, and he worked hard to develop that good relationship. And one day he gets a phone call at his desk, and one of the techs says, "Hey, Marty, there's something really strange on these batteries we're testing, and I've just never seen it before. And I thought maybe you would want to see this, being the battery engineer." And so Marty goes out there, and these batteries are designed so that when you get the go signal for the missile, piston injects the electrolytes into the chamber. So then you've got X amount of time where you've got to either launch or change the battery. So we would test these batteries to make sure that they were good in a lot of different ways, voltage capacity, and we knew that they aged out a certain way. And so we would actually, take several of them and trigger them and measure all those things. And what this guy was seeing was this funny little yellow powder around the piston that he'd never seen before. And long story short, it was a new emerging failure mode that nobody ever thought of in the failure modes and effects analysis that Marty was able to get in at that early part of the Exponential, come up with solutions to before he even had to go to a risk management meeting.
First I wanted to thank you, Charlie. This is a really great, and for us that are working in space industry, in space exploration, and building a sustainable vehicle that will be, at least right now, rated for 15 years of continuous use, with the majority of that is autonomous, is extremely important. What I did not see on your, and I'm sure that it's most likely somewhere in the future charts, that one of the important parts in whether it's a risk management or any other process, that establishing the repeatable process, and knowing the expectations. Because if you don't have this established and set up, defined, how often you are going to look at your risks, right? And what is the process of the risk assessment? And it's not just risk related, of course, it's the same, the faults assessment and so on. If that is not repeatable and expectable, the process that consistently, then it's not going to work. Ad hoc is not, unfortunately, working well in anything that you're sustainable, that you want to create. That's what I found in my experience.
Well, I'm sad to say that we rediscovered that over and over and over again with ICBMs. When we followed this discipline process I'm describing here, you know, we would maybe have one crisis a year, but if we lost our discipline, we would have multiple crises in a year. And, you know, that could easily kill a program.
Right. Well, thank you so much. Any other questions? I don't know if Larry he has his hand up and if he wants to talk. And by the way, I wanted to ask, is Larry the same as we had Larry with last name? I think it's Marklestone. I'm the only Larry. Okay. I guess it's the same. And that Larry still cannot talk.
Well, next week I may have a little more something to say and comments about your exponential process there and how that works in and what lessons are learned there. So, but I look forward to it, and I appreciate the presentation today, Charles. You did it very good. Thank you.
Thanks, Mike.
Yeah, thank you so much. And unless there's any other questions, we will end our meeting for today. Thanks for everyone that joined us, and especially Charlie. And I'm looking forward to our next Saturday, where we will hear the second part of this presentation.
Tell your friends.
I will definitely send the email. Thank you. Have a good day and good week.